Pressure and force are not the same thing. Pressure is not a force, it's force per area unit. It's also not a vector, it's only magnitude, it's just a number. Imagine if you pushed your finger on a table and you're pushing it like this. Because there's a high surface area of this table, there's a very low pressure. But what if there's a sharp knife and you push your finger on that? This surface area is super small, so the pressure is very high. It's much more concentrated, even if the force is the same in both scenarios. The standard unit you'll see for pressure is newtons per meter square. And this is also known as the Pascal. So Pascal's, named after this famous mathematician, represents pressure. Here's an example. Imagine a 70-kilo human. And he's taking a little shower. And he's standing in his shower. And the amount of space his feet cover is 400 centimeters squared. Let's find two things. The first thing is the pressure. The second thing is how much pressure if he's standing on 1 foot. Take a look at the pressure formula. P equals force over area. The force is gravity, so mg. Now let's plug in our values. He's 70 kilos. Gravity is 9.8. And the area he's covering in meters is 0.04 meters squared. So we can plug that in for area. The answer is 17,150 pascals. This is how much pressure there is from his feet standing on the floor. What if he's standing on 1 foot, so he lifts 1 foot off the ground? This means that the area is cut in half because only one of his feet is touching the floor. That means pressure doubles, giving us 34,400 pascals. A lot of the time, pressure is a pretty big number like this, and you'll see it in scientific notation. That's the introduction to pressure. Now, why does this matter for fluids? Imagine a fluid that's at rest, so it's not moving, like a cup of coffee. Fluid is at rest. Let's zoom in on this cup of coffee. The fluid is exerting pressure in all directions, always. So that's the first point. Pressure is exerted every direction. The second thing special about fluids at rest is that imagine a tiny cube, a super tiny cube of this fluid. All the pressures on all sides of this fluid must be equal. They must all balance out. Why? Because if one of these pressures were bigger, then that would create a net force and your fluid would start to move, which contradicts our assumption that the fluid is at rest. So all pressures are equal. The final thing is that pressure is always perpendicular to any solid surface. So let's say the force that pressure is creating is this way. This is perpendicular to the solid surface. But what if it was parallel, which is impossible if the fluid is at rest? If it was parallel, then Newton's third law says that it should create an equal and opposite reaction. So it would exert a force back on the fluid and make it move. So this parallel component of force from pressure is zero. It's always perpendicular. Here's a very common formula. Imagine a swimming pool. Okay, it's a swimming pool like this, and you dive in. You dive in here, and you dive in at a depth of h. That's how far down you go from the surface of the water. The pressure from the water at this height comes from the column of weight above that point. So this water here above you is where the pressure comes from. The pressure is given with this formula. P for pressure equals density times gravity times height. And if you're looking for the difference in pressure between these 2 points, there's another formula. It's the same thing, but with delta. What this formula tells us is that area is irrelevant. As long as the depth is equal, it doesn't matter how big, it's always the same amount of pressure. We're running this through an example. Imagine a water tank on one of those towers, and it's filled to the brim with water. The water tank itself is 2.5 meters tall, and that's the depth. Calculate the pressure difference between the top and the bottom. Let's use our new formula for change in pressure. Gravity is 9.8. Density for water is always constant since water is basically incompressible. And the height Change in height is 2.5 meters. Let's go ahead and solve. The change in pressure is 24,500 pascals, or in scientific notation, 2.45 times 10 to the power 4. That's the difference in pressure between the top and the bottom. Let me teach you all about atmospheric pressure. So, Earth has an atmosphere. The pressure of our Earth's atmosphere also changes depending on depth. But it's a little bit complicated. There's no set top height point, and it also varies slightly from the weather. At sea level, the air pressure is 1 atm, so this is short for atmosphere, and it's 1.013 times 10 to the power 5 Newton meters squared. You don't have to memorize this or worry about this really. It's kind of like the gravitational constant G, and I'll chuck it on the free cheat sheet in the description for you if you do like this number. Another unit is sometimes used, and this is used in meteorology and weather things. It's called 1 bar, and it's equal to 1 times 10 to the power 5. So that means the standard atmospheric pressure is slightly above 1 bar. Here's how you should think about the atmosphere and air pressure. The atmosphere is kind of like a sea of air. Remember, air is a fluid as well, because we don't exclude gases. So if air is a fluid, and fluids exert pressure depending on depth, then everything on Earth, every object, every human, is affected by the pressure of air. And finally, before we end this video, here's a quick note on gauge pressure. Most pressure gauges, like tire gauges, tell you a specific amount of pressure. This pressure that they register is gauge pressure. To find absolute pressure, you also have to add in the pressure from the air. So let's say your tire gauge says 200 pascals. The absolute pressure, you would have to add your air pressure to it, giving you the absolute pressure as 301. This makes studying 10 times easier. Go download the free cheat sheet in the description, and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.